Hello, everyone. I'm Tianxing Su, and I am pleased to introduce our latest work, GeometryCrafter, which leverages a video diffusion model for consistent geometry estimation for monocular open-world videos. In recent months, the emerging geometric foundation models empowering a wide span of 3D geometry tasks and applications, focusing on inferring 3D geometry from monocular images or videos, which typically output depth maps or point maps. The existing models are mainly fine-tuned from backbone networks, falling into two splits: VT-based models derived from models like Dino V2 and VDM-based models fine-tuned from models like SVD. Due to the inherent difference of pre-trained data and model architecture, VDM-based methods usually excel in temporal coherence and geometry detail. However, their architecture prevents end-to-end training, confining outputs to normalized representations and posing challenges to fine-tune on real data, which often suffer from missing depth regions. The first question is, why is the normalized value widely adopted in VDM-based methods? As mentioned by Marigold, the key to unlocking the potential of a pre-trained diffusion model is to keep its latent space intact. To achieve this, VDM-based methods simply employ the RGBV to encode and decode 3D information for extracting latent codes, thus normalizing 3D cues into a bounded range that is suitable for VE processing. However, normalization will inevitably lead to inaccurate geometry estimation and large distortion for distant regions, due to a large compression ratio for large values. Central to our approach is a novel point map V, tailored to effectively encode and decode unbounded 3D coordinates without compressing depth values into a bounded range. Its dual encoder architecture uses a frozen RGB encoder for primary depth information and a residual encoder to embed the remaining information, inspired by layer diffuse. If the impact of offset latent is constrained, the point map latent is aligned to the original RGB latent distribution, enabling the utilization of pre-trained diffusion weights for robust zero-shot generalization. To better encode and decode the point maps with our proposed VAE, different from previous methods that entangle the ray directions and aspect ratio into the point maps, conveying location-specific information that diverges from the translation invariant nature of RGB features. We propose a simplified representation that decouples the point map into a diagonal field of view and a depth map in log space. Given the point map V, we can fine-tune the diffusion model to estimate point maps for videos with synthetic data. The synthetic data still suffers from limited diversity in camera intrinsics, which may degrade the generalization ability. To mitigate this, alongside video latents, we propose the integration of per-frame geometry priors from an end-to-end lightweight model as conditioning inputs. Although they may suffer from inaccuracies and lack temporal coherency, they provide strong camera intrinsic clues for better generalization. Here are some visualization results of our method on open-world videos. We define the point map in the local coordinate system of each frame. Given the cross-frame pixel-wise correspondence output by a point tracker, we can obtain the camera poses and project point maps into the world coordinates. We can also decouple the static background and the dynamic foreground with segmentation masks, providing a strong initialization for 4D reconstruction or other downstream tasks. We compare our method with other representative point map or depth estimation approaches, e.g. Duster, Monster, Emogu, and DepthCrafter. Our method outperforms others on most benchmarks, producing temporally consistent point maps with fine-grained details for further exploration. Thanks for your attention. We've released our code, Hugging Face Demo, and model weights for re-implementation. Welcome to chat with us for details and further improvement.